Hi everyone, this is the second video on work for Math 1452 at Texas Tech University, which is Calculus 2. So in our first video, we kind of went through some of the basics of work, what it is, what formulas we're going to use for it. And so for this video, we're going to go into our first example on work. So our example reads that we have a cable that's 50 meters long and our cable has a density of 3 kilograms per meter. If the cable is hanging over the side of the building, what is the work done in pulling the cable up? So we know that this is a work question because it specifically says, what is the work done if we pull the cable up? So I like to start word problems by pulling out all of the numbers and then saying what they are. So the only numbers that I see here in this pretty short problem statement are this 50 and this 3. So 50 meters is going to be the length of the cable. And then 3 kilograms per meter is going to be the density of the cable. And so this density, because it has that kilograms, we know that this is the weight density. Okay, so these are the two numbers that we have. So once we can pull out the numbers and draw a sketch of the scenario where I just have this little picture here about the cable being pulled up, then we can figure out what work we're doing here. So specifically, we're trying to find the work done in pulling the cable up. So this type of work is going to be lifting objects. So that's the type of work here. We're lifting this cable up 50 feet, and that cable has a weight density of 3 kilograms per meter. So first of all, we're going to need to identify the integrand using the formula for lifting objects. So for lifting objects, our formula for force, I'm going to highlight this in blue here. So our formula for force is weight density times distance. So to find our integrand, we need to find the weight density and the distance. So starting off with weight density, this is just given to us in the question. So this is given information, and this is just 3. So we know the weight density. There's no really work to do here. So for distance, there is going to be some work to do. So you can see that instead of our 50 feet kind of vertical line here, I've instead put this on a coordinate plane and I've identified some different points. So because that distance is 50 feet, I'm going to have this bottom point here starting as 0, 0 and putting my origin right there at the base of the building. And that means that the top of the building there is 0, 50, right? So our y value increases to 50 because we went 50 feet up. And then whatever the bottom of the cable is, I'm going to have that labeled as 0y. So it's the y value that represents where the end of the cable is. So I'm going to have y because we're moving vertically. So I'm going to have y represent the height of the end of the cable. And so you can see based off of once we lift it up, y is just going to kind of track that cable as it lifts up. And if y is the height of the end of the cable, it's actually going to be the same as the distance the cable has been pulled up. So these are going to be the same distance. So you can see that y is going to correspond here with the end of the cable, but if we're also keeping track, then this is also a distance of y, right? We can see that, yes, it's where the end of the cable is, but it's also how far we've lifted it up because we're starting at 0. So that's what our y is going to represent. And so the distance is going to be the distance we have left. So our work and our forces, our distance are going to change as the object moves. And so our distance here that we're going to have in our integrand is going to be 50 minus y. So I'm going to write this down first and then explain it. So our distance here is going to be 50 minus y. And so our distance is going to be 50 minus y because if we have already pulled up y meters, then we have 50 minus y meters left to pull. So that's going to be the distance we have remaining. So at any point, we can say, well, how much more do I have to pull? And that's going to be 50 minus how much I've already pulled. So that's going to be our distance here. And so remember that our formula for force is going to be weight density minus distance. So our force is going to be 3 times 50 minus y. And I'm just going to go ahead and distribute that 3 to be 150 minus 3y. Oops. 150 minus 3y. Okay, so that's what my force is going to be. And then since the cable is going to lift up 50 feet, we can again see that my lower bound is going to be 0, and my upper bound for lifting objects is the distance lifted, so it's going to be 0 to 50. So now that we have our integral and our bounds, we're going to set up our integral as the integral from 0 to 50 of 150 minus 3y dy. And the rest of this question is just integrating using the techniques that we know from Calculus 1. So my 150 is going to turn into a 150y. My 3y is going to change into a 3 over 2y squared because I add 1 to the power and divide by the new power. And then I'm going to evaluate this using the first fundamental theorem of calculus, where I'm going to plug in my 50 first. And then I'm going to subtract, plugging in my 0. Okay, so I'm going to have that 150 times 50. You may need to break out your calculator for this one. I'm going to multiply it by 50. So I have a 0, 0, 5, 2. So that's going to be 7,500. Minus, and then we're going to have 3 over 2 times 50 squared. So 50 squared is going to be 2,500. So I'm going to go ahead and cancel this. So 2,500 divided by 2 is going to be 1,250. And then 1,250 times 3 is going to be 3,750. Okay. And then these zeros are just going to be 0. So then 7,500 minus 3,750 is going to give me 3,750 again, because that's half of 7,500. And then lastly, I'm going to have my joules. Okay, so that is what my integral evaluates to. Okay, so you can see that the actual integration part doesn't tend to be the difficult part of these questions. The difficult part of these questions is much more often the setup. So figuring out that my distance is really my distance remaining. So in this case, as the cable gets lifted up, it gets easier to lift. And you can kind of imagine this in a real world scenario that if you've ever pulled on a rope and a tug of war or anything like that, or lifted an object using a cable, it becomes easier when there's less cable. So in this instance, as you lift the cable up, then there's less cable to lift. So you're actually lifting less weight. And so you can kind of conceptualize and just kind of check this formula for force here, and that it actually makes sense. So if our cable has a weight density of 3 kilograms per meter, and it's 50 meters, then the total weight of this cable is 150 kilograms. And so as we pull that cable up, each meter we are pulling that cable up, well, then there's 3 less meters that we're pulling. So it makes sense that as we lift this cable, then there's less cable, and so the weight goes down and there's less force required to move the cable. So this y being negative makes sense kind of in the context of the question. So if that was confusing to you, hopefully that explanation helps, that as you lift the cable, there's just less cable to lift, so it becomes easier. So that's why we're subtracting based on y. So this is an example for lifting objects. That's where we're going to end this video, but we hope this helps and good luck.